T minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Ignition. Liftoff. Liftoff. 30 minutes. Control and liftoff.
Hello and welcome to another episode where we ask, what's up with the universe? I'm your host, Eli Hugh, and whether you're joining us live or you're watching us on a replay, thank you for joining. In case you haven't noticed, I actually shaved today. You thought I was going to say something else, didn't you? Well, I do want to say that today is Memorial Day. It's Veterans Day. I do remember it's memorial for me because my father was a World War II vet and he did serve at Hawaii during the attack. And I do respect all veterans. Veterans are not cowards, they are heroes. Whether you've been captured or not, you're a veteran, you're a hero. Okay, and on to that. Today, we are asking, what's up with the universe? And today we are talking about stars. Yep, stars. I mean, stars, this is basically fascinating altogether. If you want to know exactly what a star is, they are huge balls of hydrogen and helium that's formed in galaxies from great big clouds of gas and dust over billions and billions of years. If you don't already know, the stars are suns, just like our very own. Just in case you wasn't aware of that. Have you ever asked yourself, how many stars are there in the universe? Well, the best answer is to say billions upon billions upon billions upon trillions of stars, because we really don't know the exact number yet. There are different types of stars in the universe, from protostars all the way up to red supergiants. I mean, they can be categorized according to the masses and temperature. They're also classified by their spectra. It's the elements that they absorb. Along with the brightness, which is the apparent magnitude, the spectral class of a star can tell astronomers a lot about it. Stars, they are massive luminous spheres of hot plasma. If you're not sure what plasma is, there are different stages. There's a solid, a liquid, a gas, and plasma. Plasma is a gas that's so hot that the nuclei and the electrons of the atoms have separated. It's basically a hot soup. It contains positive ions and electrons. The positive ions is the atom nuclei, for all you nerds out there. They basically consist about 70 to 75% hydrogen, 25% helium, and some heavier trace elements like magnesium and gold. Yes, there is gold in stars. Of course, the composition can vary significantly, depending on the age of the star and whether it was born in the early times of our universe or just more recently. I mean, the sun, for example, our own sun, it's composed of 74.9% hydrogen and 23.8% helium, leaving less than 2% for basically all other heavy elements other than helium. Basically, this is the life cycle of our sun. From birth to what you can see it is now, it's about 5 billion years old. And after that, it's going to gradually warm up and turn into a red giant. Then, of course, it'll shed its core and turn into a white dwarf. And I will get into that in the show in a little bit. What about the star with an estimated 300 million years older than the universe? Mountains. I believe you have a wrench. If you can put that link in there where they talk about that, I'd be most interested in, I'm sure other people would as well. I have not heard about that story yet, so please enlighten us. Thank you, if you can. Now you just almost forgot where I was. Oh yeah, I was talking about our sun. Um, during most of the lifetime, stars generate radiant energy by fusing hydrogen into helium. It's a process that basically converts mass into energy and releases energy in the form of radiation of various wavelengths. I mean, in order to maintain a nuclear fission within their cores, stars have to have a core temperature ranging from, get this, 4 to 14 million degrees Kelvin. Yeah, that's a little hot. It turns out that our sun is an average sized star. The bigger the stars are, sorry, the stars are, and there are small stars as well. We found stars that are 100 times bigger than our own sun. 1 million Earths can fit within our own sun, and there are stars way bigger than that. Let me show you this here, right here, for example. This is a size comparison of our sun compared to Rigel, Sirius, Aldebaran, and Betelgeuse, or as other people want to say, Betelgeuse. Yeah, these are some enormous stars here. For what we know, we have studied, there are 7 classifications of stars currently. Sorry, wrong one. That means basically it's an O. Sorry, there's an M from smallest to largest, M, K, G, F, A, B, and O. And you're asking, did I just say random letters? No, not really. I'll tell you what these mean here in a moment. These basically, they range from blue to white to orange to red. I mean, they all have different, every single star has different size, has different temperatures. The main spectral type of stars are the O, which are blue stars, B, which is also a blue star, A, another blue star, F could be blue or white, G could be white and yellow, like our sun. Our sun is a G star. K could be orange and red, and M is a red star. This right here is the Hertzsprung-Russell diagram. Yes, I forgot to exactly tell you who exactly this guy was, but I mean, the smallest stars, also called the M-type stars, are just mass enough to initiate nuclear fusion in their own core. If they were smaller, they would be called brown dwarfs. Basically, brown dwarfs is about the size of Jupiter in our own solar system. With increasing mass, stars change in size, luminosity, color, and fusion rate itself. A star like our sun here, like I said, it's called a type G star. It has a yellow color, and the fusion rate allows the star to live around 10 billion years or so, so it's not going anywhere soon. Don't worry about that. The sun's going to be there. It's going to give you a nice little tan in the summer. It's going to wind up in the wintertime. It's still going to be there. Don't worry. An M-type star can have a stable energy output for about hundreds of billions of years. I mean, at that range, at the other end of that range, we have the most massive stars, which are O-type stars. These stars have a mass of about 150 or more solar masses, and that is heavy and huge. Well, of course, because of the high color surface temperature, they have a blue color, and they are also huge. Let's see, stars that have a mass of more of 8 solar masses finish their lives within a spectral explosion of a supernova. Yeah. Stars of more than 20 solar masses may even collapse into a black hole. Of course, all different types of stars can be displayed in a chart called the Hertzsprung-Russell diagram, like I showed you before right here. We're going to be right back after this little quick commercial break.
Hey guys, LDG Pixels here. You have issues with your computers? Have any IT questions? Come join us at YouTube at LDG Pixels. That's on YouTube, LDG space Pixels. I'm live. I'm here to help. Tech news, nerd chat, help you fix up your computer free.
Oh my gosh, getting invaded by a mouse here. Whoa. Okay, that was kind of scary. Oh, thank you, Mountains of Elysium. If anybody is interested in that link, I will watch it after this show here. He says it's called the Methuselah Star. Spelling may be wrong or incorrect, but that's okay. That's what spell check is for, ducking spell check. And yes, you are correct. The red dwarf star is the most abundant and longest lived, but put out more infrared than visible light. That's why we can't see St. Bernard star. Yeah, we have a hard time seeing that with our own little eyes. So, let's explain how stars are actually formed here. There's something called protostars. Yep. Oops. Protostars. The antennae galaxy shown in the visible light in the Hubble image right here. They were studied with the ALMA telescope, revealing extensive clouds of molecular gas. As you can see in the center right image. These are all zoomed in right here, of course. One cloud on the bottom image is increasingly dense and massive, yet apparently star-free, suggesting it is the first example of a prenatal global cluster ever identified. And try saying that 10 times fast while drinking hot chocolate mixed with coffee. Sorry, I gotta have my chocolate. The other kind of star formation is the T Tauri star. A T Tauri star is a stage in the star formation and evolution right before it becomes a main sequence star. This phase occurs at the end of the protostar's phase when the gravitational pressure is just holding the star together long enough is the source of all its energy, of course. But they don't have enough pressure and temperature at their cores to generate nuclear fission yet. But they do resemble main sequence stars at about the same temperature and a little bit brighter just because they're larger. As you can see the animation below on the left-hand side, the T-star HH30 shows bullets of material propagating along the jet. The middle one is an infrared image, something that our own eyes cannot see. The prototype T-Taurus star, the T-Taurus star itself. You can see wisp of dust and gas that comes from the nebula, which formed the star, can also be seen. And on the far right is a very high-resolution infrared image of the T-binary system. The little faint companion to T-Tauri can also be seen right there on the south and north. They were actually named for the first type stars, which mean variable stars. They are newly formed and about 10 million years old, and about 3 solar masses, with about a temperature, with a central temperatures too low for nuclear fusion, and basically have started. About another 100 million years, the emitted radiation will come entirely from the gravitational energy released as the star contracts under its own self-gravity, forming its own little star, pressure. The nearest T-star to us is in the Taurus Ophiuchus molecular clouds. They're about 400 light years away from us. Yeah, a little neighborhood. Some people wonder, hey, how are stars exactly made? Well, it begins like we talked about with the massive dusty cloud and it starts to collapse. It's called nuclear fission. I know, some people's like, I don't understand nuclear fission. I'm not a nuclear physicist. Well, let me try to explain this simply as I can. Fusion happens in the very large clouds called nebula. not nebulae, nebula. Of course, when nuclear fission starts in a nebula and reacts with a temperature of over 10,000 degrees, the star begins to form. Yeah, the new little star, as we know it, is then called a protostar. Then the stars are that star can live its very long life in the universe. Of course, like I said, gravity continues to play a part in the star's birth and life cycle. The mass of the star determines the color of the star, which allows scientists to categorize the type of star. They can also then try to confirm the amount of energy the star gives off, whether it's good radiation or bad radiation. Good radiation means that's another chance for scientists to actually, hey, let's see if there's anything in the habitable planets that are actually capable of holding life. Because, like I discussed before, there are some planets in the habitable zone that the radiation from the sun, from their own star, would be damaging to the planet like if it was to us. And what the hell are you doing, dude? What the hell?
Hey, what's happening? This is Coronemic. I'm talking to you from my backyard. Just signed up for Cameo app. Sean asked and told me that's what all the cool kids are doing. So I'm just trying to be one of the cool kids. But I am dedicated to this. Dedicated to leaving you a message, no matter what the conditions are. That's why I'm doing this in the rain, to prove to you how serious I am about this. I mean, I will give you a shout out from a train. You know, I'll give a shout out to you while I'm on a plane. I'll give a shout out to you from a car. I'll give a shout out to you from a dive bar. In fact, I heard that David Faustino's on here as well. He said that he was going to give some weird and creepy shout outs, but I challenge him. You want a weird and creepy shout out? Came to the right place, buddy.
Dude, man, I'm getting invaded by Anonymous, Corin, sheesh. Well, I was actually talking about the nucleus of a star. Okay. I was going to tell you that in the hot and dense cores of stars, two protons, a proton is the same as nucleus of a hydrogen atom, they sometimes crash into each other, forming a very unstable element called helium-2. Of course, normally this element almost immediately decays back into two protons. But once in a while, during the extremely short period which helium-2 exists, one of the protons decaying into a neutron, emitting a positron. Yes, the electron's anticipation for. In other words, it's an antimatter compound and a neutrino at the same time. This is how we get sunlight. The stars, they basically vary, like different types of stars. They're categorized different colors, as I said before. The four star sizes that are smaller type stars, these are called dwarf stars. You have white dwarf, brown dwarf, red dwarf, yellow dwarf, and of course, we also have the giants. We have blue giant, orange giant, red giant. We have a blue supergiant, blue hypergiant, red supergiant, and a red hypergiant. The last 7 stars are these categories. They're called large stars. Some people want to ask themselves, hey, what exactly is a white dwarf star? Well, I got a little basic comparison here. A white dwarf is very hot, very small, and very hot. It's the last stage of the star's life cycle, like our own sun, the G star. They're similar to the same mass as our sun, but they're about 1% of the sun's diameter, which means they're 1% smaller, about the size of the Earth. And they have the same mass, of course. It's very hot. It's about 8,000 degrees Celsius or more. But being small and hot costs the white dwarf a bright luminosity, which means it's only 1% of the sun's light itself. Yeah, I know. There's a downfall for everything. Of course, we have brown dwarf. For example, brown dwarf Gliese 2999b. Brown dwarfs, they are staged differently altogether. I mean, they're not officially a star, not officially a planet, but somewhere in between. Kind of like Jupiter. People say Jupiter was a failed star, failed brown dwarf, became a gas giant. But they're about the same size. Brown dwarfs are about the same size of a large planet, like I said, Jupiter here, of course. There's also this diagram here. This was taken by the Palomar Observatory on the left, and the right side was the Hubble telescope with the Wide Field Planetary Camera in 1995. I know, I'm still waiting for the James Webb. But there are also different kinds of other dwarf planets. You got the red dwarf. Those are the most common stars in the Milky Way galaxy. Actually, yeah, just like Mountains of Elysium said. The red dwarfs are the most common. They are larger than white and brown dwarfs, but smaller than yellow dwarfs like our sun. The closest one to our Earth is called Proxima Centauri. That is a red dwarf. There's also yellow dwarfs. No, I'm not talking Munchkins. I'm not talking Lord of the Rings yellow dwarfs. I'm talking yellow dwarf stars. They are main sequence stars, which means that they are in a stable range of the life cycle. I mean, our sun is a yellow dwarf, so yellow dwarfs are similar in the size of our sun, and they're about the size between red dwarfs and blue giants in the south. Of course, blue giants, they're the smallest of the 7 largest type of stars, and larger than yellow dwarfs, believe it or not. There's also orange giants, not the drink. Orange giant, not the baseball team either, but still. Orange giants are stars that are sized between blue and red giants. There's the star called Pollux is an orange, best example of an orange giant. With the orange coloring indicating that the surface temperature of the star is lower than the main sequence star. And of course, we also have our blue supergiants. Yes. Blue supergiant stars. They're between the size of red giants and blue hypergiants, and they're very hot and very bright. As you can see in the comparison here, the sun is a main sequence star. It's a little tiny white dot in the center. And of course, you have the other one. That's as far as your Earth orbit is. The blue supergiant can go to about the size of Jupiter's orbit. It's 1 AU in diameter, well, less than 1 AU in diameter. Yeah, that is a huge star. But red giants are the largest luminosity stars, but they also have low mass. And they are in the late stages of the cycle and have burned out most of the hydrogen at the core. Speaking of red giants, there's also a red supergiant. Would you say mountains? No star observed through the... Though if there are stars older than the universe, then they may exist unobserved. That's true. We only know about 14.5 billion light years that we can see so far. We're not sure if light actually extends that far, or if that's as far as light can actually extend itself. We don't know yet. I mean, we need to put a telescope halfway throughout the galaxy to be able to see that, at least. But the James Webb is supposed to be able to see farther than the Hubble has actually seen. Speaking of Hubble, some guys at ALMA, who were responsible for Hubble, took this picture. This is the red supergiant Betelgeuse. Yes. It is the 10th brightest star in the night sky. And after Rigel, it's the second brightest in the constellation of Orion. If you're looking for Betelgeuse, it's the shoulder. Yep. It's a huge-ass star. And some people say it's going to go supernova soon, but scientists estimate about another 5,000 to 10,000 years. If you remember a while back, there was a story going around about how Betelgeuse was dimming, thinking that it was going to go into a supernova. But that did not turn out to be the case. Some scientists predicted that it was a light, thin dust cloud passing between our field of view, which turned out to be correct. I know. I don't have my 3D image to show I don't have my 3D model image installed on my computer. Otherwise, I would have showed you some rotating stars. I actually have the files on my computer, but I don't have the program installed yet. I cannot find one compatible for Mac. Yes, there are flat suns out there. Yeah, baseball team, basically. Oh, let's get back to the red hypergiants. Red hypergiants, they're the largest discovered stars in the universe so far. So far. Red hypergiants generally have a shorter lifespan than other stars and extremely luminous and very extremely large. The largest one we know of is about 1,600 times wider than the sun. That is freaking huge. Freaking huge. What happens after the sun goes to a red giant? Well, it could turn into a supernova. Yes, most small red giants die as a white dwarf, but the massive red giants die in a more spectacular way, a supernova. Didn't you just type this here, mountains? I know. I didn't pull it up yet because I haven't got to that part yet. Spoilers. I mean, after the feel of a red giant is exhausted, the core becomes cooler, and the internal pressure begins to decrease, causing contractions like a pregnancy. For massive red giants, this is a disastrous event, of course, which leads to the collapsing of the star. But the good thing is the outer layers start to gain heat as they fall, and the heat ignites nuclear fission in the outer layers, which causes them to explode. That's the good thing, it explodes. This is called a supernova. This is Kepler's supernova. This supernova occurred in the Milky Way and is the most recent supernova to ever be seen by the naked eye. And a supernova itself. It's basically an explosion of a death massive star. It could be seen as bright as 100 million bright stars. Yeah, that's huge. It's very bright. Make sure you have some shades on if you're close by. Supernovae have been accounted for creating heavier elements other than hydrogen and helium. And over the years, two types of supernova have been found, a type 1 and type 2. The type 1 happens in a binary star system and occurs by gas from one star falling into a white dwarf, causing it to explode. The other one, which people love to watch and sky gaze and watch, is a type 2 supernova, which occurs when a humongous star, at least 10 times more massive than our sun, like Betelgeuse, explodes. It becomes a malfunctioning internal nuclear reaction. Yep. These large explosions either cause a neutron star or a black hole. Supernova to a neutron star, how this happens is the outer layers, they're blasted off into space from nebula, and we see beautiful colors of different gases that was exposed within the sun, and some that was actually created. But the core itself, it's shrunk by gravity and condensed into a sphere, the shape almost the size of Manhattan. Yeah, and that is very, very heavy and dense. The EM force basically keeps the electrons out of the nucleus. I mean, since the EM force is the only thing that matters, the star wouldn't be able to shrink to such a size simply because of the mass and number of atoms. However, because of the star's mass, gravity itself defeats the EM force. And since the EM force is now broken, the protons and electrons combine to make neutrons. And all that is left are neutrons. And this is how our neutron star is formed. Hey, if you guys are actually wondering, how do I go about looking at stars myself besides just looking up and see what I can see? Well, there's a couple different apps out there that you actually can download and look at yourself. There's one called Star Rover. I know it costs $2. They're not paying me to promote this. It's just some stuff I found. It costs $2. It's for the iOS and Android. It's a great app to learn basically about constellations. To use it, you just need to put your smartphone towards where you want to see in the sky, and it tells you exactly, basically, pretty much what you're looking at. There's also called Sky Astronomy, and oh my gosh, I think I cut it off, but I'm going to put these links in the bottom of the after the description here. What'd you say, mountains? Magnetars are supposed to be among the smoothest objects in the universe. It has crushed the space between atoms. Yes, I've got to talk about magnetar stars. Thank you, mountains. Oi, what would I do without you guys? Go even crazier? Nah, maybe. Possible. Who knows? But I'm talking about Sky Astronomy, the little app. This is one of the basic ones here. It's a free app. Yeah, this one is free. It helps people who has telescopes by providing a push-to guide for easy navigations. It comes with a time machine feature that you can actually use to foresee the future stars, how they move, or how they were in the past. This is for basically anybody who has a telescope and wants to know exactly what they're looking at and how to look at it. Another one for all you moon watchers out there is called Deluxe Moon HD. Yes, it's on the iOS platform. It's in different languages. It comes with a traditional lunar map with up-to-date technology, giving you feature-rich content with a much-needed flair. I love that. I had to quote that. Sorry, I even have this on my phone. It basically tells you moon phases, the name craters, and everything. It's a pretty cool app. It's free. We also have Sky Safari. Space is fake. LOL. I know. That's why I don't type with space bars. I just put all my letters together. Oh yeah, I was talking about Sky Safari. You can simulate the night sky from anywhere on Earth, anywhere. Many years in the past, the future, a little time flow feature. It uses NASA's spacecraft and the Hubble telescope's data, so it's actually up to date. You don't have no randomness there telling you, oh, this could be this star, this could be this constellation. But if it's verified by NASA and Hubble, then they actually verified where it is in the sky. It also gives you images of planets and their moons. So if you want to know more about planets and moons, like Jupiter's or Saturn's moons, Sky Safari is a good one for you. And it also helps you know when upcoming meteor showers are happening. There's also the, many people are familiar with this on the Android platform called Sky Map. Yeah, it was originally developed as a Google Sky Map. Basically, use your phone to track your GPS, keep your locator on, and just move your camera around and it'll tell you give you a live update of where the stars. You can do it on constellations, you can do it on planets. It's a little generic one. It's for the Android platform as well. My favorite one that I use is called Stellarium. As you can see, I even have the web link up there, stellarium/web.org. It's for Android, it's for PC. Your iPhone is for your Android phone. It's all platforms. It's a totally free service. What I like about Stellarium is I see moving light in the sky. Well, I click on it and tell me what exactly it is. And when I clicked on it this morning, a Starlink happened to be passing overhead, and I clicked on that and it'll tell you exactly what the satellite is. If it's a classified satellite, it'll tell you classified satellite, because everything up in orbit tracks itself. Everybody, there's a tracking of everything in orbit. You may not know what is up in orbit, but there is a way to tell you exactly where it is. I love this website. I'm going to put these descriptions of these little star finders and sky maps and everything for you guys after the end of this video before I upload it to you guys. So in case you're watching later, hey, scroll down. Oh, you scroll too far. You forgot to hit the subscribe button and the bell. Yeah, okay, thank you. Now scroll down even further. You'll see the links for the NASA and the apps. Okay, cool. And before you guys go, I just want to thank you, everybody here. And we're going to play a little, I'm going to show you a little size comparison before we take off. So I want to thank everybody for joining me, and you guys have a good day. And veterans are heroes. Hug a vet, if you can, virtually.